sir.
Is this slide moving?
Yes, sir. Yes, sir.
Okay, fine. So let's start. So the thing is that I will discuss about the self-excitation technique in a MEMS resonator. That means all of you know that suggesting to use MEMS technique to build the resonators for oscillators application is not something new. That means you will find so many applications of MEMS in different field. This is called electromechanical systems. Also, it is known as micro machines in Japan and microsystems technology in Europe. And it is microfabricated system comprising of both electrical and mechanical components. That means there will be electrical and mechanical components, both will be there. And it is a miniature device which actually used to convert one energy from another, either from electrical energy to mechanical or mechanical to electrical, like that. And also the typical dimensions of such system ranges from hundreds of nanometers to millimeters. So there are several applications of the MEMS. So it is, you first know that about this thing, that it is a device made of some mechanical component and electrical component. So we will further discuss about this MEMS, how it works, and what is the function of that. So first we discuss about the what is the actually function. That means what is the function of the MEMS, where it is used. The main use of MEMS in many devices is like to sense the pressure, acceleration, force, temperature, mass change, displacement, vibration. The advantage of this device is like that it is a miniature device. You can place these devices in any component, whether it is a small electronic circuit, whether it is a small any experimental devices or any vehicle, anywhere you can place it because it take less space. So it is used to measure any kind of data, not only limited to those pressure, acceleration, forces, like that. Also, you can extend these things to so many applications. Also, it is used to sense, and also it is used to actuate. It is used to actuate some systems. Suppose you can convert the electrical signal to mechanical movement. Suppose you are giving some voltage or some mechanical system will oscillate, like that. So you can actuate any system by using of the MEMS actuator. So in both cases it can be used. And most common type of the MEMS actuator, you can see electrostatic, piezoelectric, thermal, magnetic. So there are several types of MEMS actuator. So we do not discuss about those types in details. But first, we have to understand about the MEMS clearly, that how it works and why we will use this MEMS. So next is the it is also what are the component used in MEMS. If you think in component, you can say that for the electrical system, it is for electrostatic, it is one capacitor is used, a very small capacitor, electrodes from a capacitor. That capacitor, that means if you connect a capacitor to a mechanical system, if the display, it is connected in such a way that if a mechanical system changes its displacement, then the capacitance of the capacitors changed. So this change actually sensed, and we measure the displacement of the mechanical system. This is the way. That means you connect a capacitor to any device, and that device, suppose if you consider a pressure, if pressure changes, the capacitance also changes, and that change actually helps to identify or to determine the value of the pressure, like that. It works in this way. So different application, you can say it is in consumer electronics. Consumer, in mobile phone you will find this. When you rotate a mobile, it actually detects by using the gyroscope. And smartphone, laptop, tablet, in everywhere you will get the MEMS, you will find the MEMS. Also in microphone also MEMS are used. For example, when a phone rotates, MEMS accelerometer changes capacitance and microcontroller adjusts screen orientation. That means how it works. Suppose you rotate a phone, and when you rotate a phone, then the rotation actually sensed by the mobile capacitance, and the capacitance changes, and this change actually tell the microcontroller that we have to rotate the screen of the mobile, and as a result the mobile screen rotated. Similarly, automotive application, airbag sensor, when it strikes something, the vehicle strikes something, the airbag sensor actually sense that sensor actually use the my MEMS. It MEMS helps to sense the strike. Tire pressure monitoring system, engine pressure, internal measurement units, crash detection, so many applications. But nowadays it is very useful for the biomedical application, where you can find microfluidic devices, lab on chip, to detect any report on that thing. And next is the industrial and robotic application, where you can use MEMS as a vibration sensor, flow sensor, pressure sensor, like that. Also, it is there are very much use of MEMS in communication system, where RF MEMS switches, micro resonators, timing references, etc. In those cases, it is used, and also defense and optical application it is used. So these are the different applications of the MEMS. Now, next. Types of MEMS by operating principles or sensing mechanism. Generally, what I have written here, those are the different type of MEMS working principle. One is capacitive. That means a capacitor is used. That capacitor, actually the capacitance of the capacitor is changed when something happens. That means when displacement occurs, or when acceleration changes, like that. So with the change of the capacitance, we measure the acceleration or displacement or velocity or pressure, etc. So that is a type of electrostatic MEMS. It is called electrostatic MEMS, where electric circuit and a capacitor is used. And now piezoresistive and piezoelectrics are more popular nowadays. Piezoelectrics means when you there are some materials, when you apply some force on that material, it actually generates some electric signal, and the change in displacement is proportional to the generation of the electrical signal. So when there is a change in a displacement, there is a generation of the electrical signal, and from that voltage you can measure the change. Also, vice versa is possible. That means if you provide some electrical signal, the material will change its deflection or length. So by putting the voltage, that voltage is proportional to the change of the length. So by putting the voltage, you can measure the or you can actuate any system. Some is electrostatic, use electrostatic force for actuation. All of you know about the electrostatic force that is also used. That is from old days. It is in most of the MEMS device you will find electrostatic type MEMS, right? And there is also magnetic MEMS. I have not written one thing, that is optical. Nowadays, optical also use optical MEMS also used, where optical things are used to actuate the or to function the MEMS. Okay, these are the types of MEMS. So this is the MEMS. Now these are the materials. There are so many materials for different application. For structural, you can say the silicon is the most popular, most common is the silicon. And besides those materials, also nowadays research is going on crystal. Actually, to develop the MEMS with crystal is very difficult. So, but nowadays it is very popular. That means the researchers are using crystal to develop the MEMS. And besides this, there are so many materials you can see in the slide. That is silicon, also conductive material, aluminum, gold, platinum, metal MEMS, nickel, copper, and polymer materials, MEMS, PDMS, etc. And piezoelectric material, what I'm saying about this, that PZT is the most popular, lead dichromate titanate. Besides this, ZNO and AIN is also there for the piezoelectric material. So these are the material which are used to fabricate MEMS. Now you have to understand the how the MEMS works. You can see here in some animation. From that you can understand that how MEMS work. Suppose first one I am showing you that look at this thing. That one is first one is the piezoelectric effect. What I'm trying to say before that here you can see that if you apply some force on a material, particular material, and when there is a deflection, it generates some voltage. So that can be used to actually sense the or to detect the displacement, because by measuring the voltage, voltage is actually proportional to the displacement. So by measuring the voltage, you can change the displacement of this material. So you can place this material on any system so that you can measure the displacement or acceleration, etc. Also, vice versa is possible. Vice versa is possible. How you can see that when you apply some voltage, the material elongates. So that is also can used for the actuation. And where it can be used, suppose on one example, you can see that that is the MEMS speaker, piezoelectric MEMS speaker. When you talk, there is a you actually are producing some signal, and it strike on the microphone. It strike on the surface of the microphone, and a piezoelectric material is placed on the surface of the microphone. So it is compressed. So when it is compressed, it generates some signal, and that signal can be used to actually to clear or to nullify the noise and to clear your voice, that means in the microphone, that so that it can be audible. Your voice should be audible in a microphones. Okay, so that is the thing, that in a MEMS microphones, air vibration, if that is your talk, air vibration heat a membrane and vibrate. And the piezoelectric material converts these force into electricity, which can be used to extract sound as an electrical signal. That means the sound can be extracted as an electrical signal. That is a simple example. So you can see it is a particular MEMS where there are no oscillation. There is no oscillation. Just you can say that you are applying some force, constant force, and that force hits some membrane, and that change in displacement of the membrane actually detects the is detected, and it generates some electrical signal. So your voice is converted to an electrical signal. That's all. Now, a particular type of MEMS, which we are coming now, that is called the MEMS resonator. Now, in this case, the system will oscillate. What happens in MEMS resonator? In this system, a micro-messing device which actually vibrates at its own natural frequency, and which will be excited by an external force. So here you remember that a MEMS resonator, the system will oscillate, and it oscillates at its natural frequency, and this oscillation is generated by some external force. It may be some electrical voltage, it may be some any other thing. But the thing is that to generate the frequency, to generate the oscillation at its own natural frequency, you have to know the system's mass and the stiffness. So when you know the mass and stiffness, you know the natural frequency, and you can provide the oscillation, the external force frequency same to that, so that the system will oscillate with the natural frequency. So you remember that thing, that whenever you are using a MEMS resonator by an external force, you have to know the natural frequency of the system, and you have to provide a external force, specifically a dynamic force, which can create the oscillation. That means static force cannot create the oscillation. That is the thing. Next, what will happen? These devices are used in application like timing, filtering, or sensing. They offer some advantages like small size, low power consumption, etc. And it can be used as a transducer as well as it can be used as a actuator. So now next is the working principle. I'm discussing this thing a little bit, that working principle, how it works. First, a input electrical signal is applied to an electrode near the resonance structure. A signal is applied to an electrode near the resonance structure, and then this creates an electrostatic force that pushes the resonator and it causes the vibration or oscillation. That means you are generating the oscillation by help of an electrostatic force. And remember that force should be dynamic. That means you have to provide some AC voltage. As the resonator moves, it changes the capacitance between itself and another electrode. So there will be another electrode, and when the system resonates or the system oscillates, it changes the capacitance of the resonator and it generates some electrical signal at the resonant frequency. Now, how it will work? Suppose it work, the resonator is on and it is oscillating at its own natural frequency. Now, some pressure, for example, some pressure is applied on the system, mechanical system. Suppose it is a mass spring damper system, or it is a cantilever beam. So cantilever beam is oscillating at its own natural frequency, and you are applying some oscillation frequency. Now you are applying some pressure on that cantilever beam. So when you apply some pressure on that cantilever beam, the stiffness of the cantilever beam will change, and as a result, the natural frequency of the system will change. So the oscillation frequency also change. As a result, the capacitance also change. So that change will help to measure the pressure. That is the case. Here what I have discussed, that is actually shown here. You can see in the figure that the membrane is oscillating at its own natural frequency. Suppose now a pressure is applied on this membrane, so it will change its stiffness. So its own natural frequency also changes. So when its own natural frequency will change, that is sensed by the change in capacitance, and as a result, it will detect the pressure. So it is not only for pressure, it may be happen for the displacement sensor, for the acceleration sensor, like that. So that is the technique, or that is the thing for the you can say that for the MEMS resonator. So you have understood that first term is MEMS. MEMS does not mean this, that is it is a resonator. MEMS means it can used for sensing or actuation. It may be resonator or may not be. Now, a particular type of MEMS is the MEMS resonator, where the system oscillates. That is clear. Now, to oscillate the system, we have seen that we have to provide some dynamic force. That is, here it is AC voltage. So we have to provide an AC voltage to generate the oscillation. Without providing dynamic force, you cannot generate the oscillation. That is in practice, actual practice. But recently, only few works you will find where you can generate the oscillation with a DC voltage. That means with a constant voltage. You do not have to provide any dynamic force. With a constant force, you can generate the oscillation. But the thing is that here it will be a self-excitation technique. So that is the thing, that is the main topic of today's talk, where I will show you that how to generate the oscillation in MEMS resonator without applying any external dynamic force. So that is I will talk, that is the called, here I will show you a particular method which can be used to generate the oscillation in a mechanical system with a DC voltage. So that is called stiffness switching self-excited MEMS resonator. So the main thing what we are doing in this system, that we are providing the voltage, static DC voltage, that is the constant value, but with an on-off method. That is the on-off method. That is, one time it is on, then again off, then on, then off. And that on-off switching is done by a feedback mechanism. So you can see here that it is a mass spring damper system, which you know already, mx double dot cx dot plus kxt. That is the mass spring damper system. And this mass spring damper system, you can say that is the mechanical system, and that mechanical system is placed between two electrodes with a gap D. And a polarization voltage is provided having the magnitude Vp. Now, what we are doing, we are doing some feedback mechanism where you can see a on-off method or on-off strategy we have applied by a discontinuous function, which is here you can see a Heaviside step function. That means h rho here x and x dot. So h rho is 1 when rho is greater than 0. That means x dot when greater than 0, that means it is 1. Otherwise it is 0. So x is what? X is the displacement of the mass and x dot is the velocity of the mass. And x0 some initial value or reference value we have selected. So when this term within the first bracket is greater than 0, then the voltage is on. And when it is less than 0, then the voltage is off. And in this function, that the right hand side function APH, that AP is the net electrostatic force, which you can see given by this expression. We are not going details about how to derive this expression. This is the expression where you can see there is a Vp, which is a constant voltage, and x is the displacement, D is the gap, and C0 is the capacitance. So this AP, electrostatic force, that force sometimes on and then again off, then on, then off. And in this function, you can see there are no external frequency we are providing. And this is a function of only the displacement of the mass, that means x. So this force function is a function of the state of the system, and that is the reason why it is called self-excitation mechanism. Though we are providing in a feedback, we need some power, we need some controller like that, but as the forcing function is not the external, it is internal, so we are saying that it is a self-excitation mechanism. So with a constant voltage, we can generate this self-excitation mechanism. You can see in the second figure that when x dot less than 0 and x0 is less than x absolute x, then the stiffness of the system actually lowered to lower value, and otherwise the stiffness remain the stiffness of the system mass. So now we will see that the output of this system, how it respond if we simulate this system and if we analyze this system. So first thing what we have done, we have simulated this equation in a MATLAB Simulink, and we see that for a particular value, okay, before doing the simulation, this is the equation of motion, then we have converted it into a non-dimensional form. So you do not have to know the non-dimensional form. You can see we have converted this equation to another equation, another second order differential equation, and there will be no loss of generality. And why we do the non-dimensionally? Because to reduce the number of parameter. You can see that in the first equation the number of parameter, and it is more than the number of parameter in the second equation. So we do the non-dimensionalizing to reduce the there is a oscillation. There is a pure oscillation, and because it is a closed circle. When in a phase plane, it shows the closed circle, that means there it is a oscillation. Sometimes it is also known as limit cycle oscillation. You remember, limit cycle oscillation is nothing that of oscillation. Limit cycle means it's a oscillation. So it is as it is a closed boundary, so it is a oscillation. So it can generate some oscillation. Now, next, now the question arises that is it possible that for all value of gamma, the system will oscillate? Now, that thing we have analyzed, and we can show you here that when only pure oscillation occurs, for what value of gamma. So you can see here that we did the nonlinear analysis. From that, we can calculate the amplitude of oscillation, and you can see that in this equation, in the main equation, the coefficient of y in the left hand side is 1. That means the natural frequency of the system is 1. And also, we have done the averaging, and we see that amplitude of oscillation is given by A, and frequency of the oscillation is 1. That means it is equal to the natural frequency of the system. So you do not have to do anything. You are using this system, it automatically generates the natural frequency of the system. You do not have to provide any external force with the frequency equal to the natural frequency. So you do not have to worry about the value of the mass or the spring stiffness. So it will automatically generate the natural frequency of the system. That is the actually advantage of the self-excitation mechanism. Also, we have analyzed that the operation value of the gamma is actually should be between these two terms. That means y minus y0 square less than equals to gamma less than y minus y0 square by y0 square. So that gamma value, lambda value, lambda is nothing but equals to 2 gamma by pi zeta. So that lambda value should be between these two values to generate pure oscillation. So that is the limitation, actually, you can say, of this self-excitation mechanism. For all value of gamma, you cannot generate the oscillation. You have to choose or select the value of gamma or lambda within this range. That is the drawback, or you can say, or the limitation. Now, how the oscillation occurs, we will see now. Now, we have plotted the oscillation nature or transformation of the phase plane in the parameter plane y0 and lambda. Look, gamma means it is a function of voltage. So you can say that gamma means voltage, or lambda means it is actually indicating the voltage. Also, zeta is related to that. So you can say the y-axis denoting the constant voltage, and the x-axis is the y0, which we have considered in the reference value, Heaviside step function. You can see within the first bracket there is y0. So here you can see so many possibilities are there. If you select, within this region, then you can see there will be no oscillation. It is going to static equilibrium. That means if you provide these values of the parameters, then there will be no oscillation. The system will not resonate. On the other hand, if you consider this region, you can see there is a closed circle, but it is a dotted circle. That dotted circle means it is an unstable limit cycle. That means unstable oscillation. You cannot generate in actual practical application. It is present theoretically, and so this is not desirable. This unstable limit cycle not desirable. It will actually hamper the system. So also within this region, you can see there is a solid closed circle and a dotted closed circle. That means both stable limit cycle and unstable limit cycle present. Again, I'm saying limit cycle means nothing but the oscillation. So both stable oscillation and unstable oscillation is present. So we do not want any system with unstable system or unstable system. So this is also not desirable. Only the suggested operating region is this one, where you can see that only stable limit cycle you can generate. Only one stable limit cycle you can generate. That means the oscillation you can generate, pure oscillation you can generate. There will be no unstable oscillation. That means the system is stable. So that is the advantage. And so, some bifurcation is also shown. What happen if we change the value of voltage from 0 to 1.4? You can see from 0 to 0.6, there is no oscillation. From 0.6 to 1, from 0.6 to 1, there is a presence of the unstable limit cycle as well as stable limit cycle. So there is within this region 0.6 to 1, you can see that is a presence of the unstable limit cycle and stable limit cycle. That means unstable oscillation and stable oscillation both are present. Both are present. So that is also not desirable. From 1 to 1.4, we can get the pure oscillation, stable oscillation, pure stable oscillation. So this region we can use to generate the oscillation, or we can use in a MEMS resonator. That is another for other parameter value. The previous one is for y0 equals to 0.65, and this one is for y0 equals to 0.8. 0.8. So this is the case, and that is also for zeta equals to 0.01 and y0 we are reducing. When we are reducing the y0 value, then we can see that pure oscillation region actually increases. So that is desirable. More we are decreasing the value of y0, the greater the region of the pure oscillation, which actually desirable in a MEMS resonator. And next thing is the time period of oscillation. We can see that with the change of the value of gamma, the change of the time period or frequency. Time period means frequency, you can say. So the change in frequency is negligible. It is almost near to resonance or 1. So whatever the parameter value you are giving as an input in the system, it is actually independent, or the frequency of the oscillation is independent of that parameter value. It always remain near equal to the natural frequency or very close to the natural frequency. So you all do not have to worry about to generate the resonance or the natural frequency oscillation or modal oscillation. So that is the advantage of the self-excitation technique. So finally, I have shown you a small example to generate self-excitation in a MEMS resonator. And now the question may arise that, sir, why we use this self-excitation technique rather than we provide the external frequency force, that means the dynamic force, so that we can generate the oscillation. The reason is that there are some advantages of this self-excitation technique. The first advantage is that that you do not have to know the value of this mass or spring stiffness of the system. Whatever the self-excitation you are using, it generally provide you the natural frequency or oscillation with the natural frequency. There are some exceptional cases, but in most of the cases in a self-excitation techniques, you will get the natural frequency oscillation. So you do not have to worry for that thing. Then the it reduces the control cost. When you are using some external force and when you are using some self-excitation techniques, it has been seen that in self-excitation technique, the control cost is lower than the external forcing frequency. Also, another advantage is there. Sometimes in resonator, only oscillation is not desirable. Sometimes there are some application of chaos. It is very easy to generate chaos or different type of oscillation or different type of nonlinear dynamics in the system, which you cannot generate or develop by using the external force. Okay, for example, if you consider the washing machine, in washing machine actually chaos is required. So that chaos you can generate by using the self-excitation technique easily. So that is the advantage. And okay, and this is, you can say, here it is used or it is developed by using the using a discontinuous function. The self-excitation is developed in a discontinuous function where the voltage is on-off technique, switch on-off technique, and with this switching technique, you can change the stiffness of the system. Stiffness also continuously on-off technique or lower or higher value. As a result, excitation generates. That is the advantage of self-excitation. I have reviewed some paper, and I have seen that very few work are there where self-excitation techniques are used in a MEMS resonator. In most of the MEMS resonator, you will find that there are some external dynamic force. Few example we have seen that optical self-excitation, optical band gap excitation, thermodynamic feedback of a piezoresistive resonator, radiative pressure feedback. These are the technique different self-oscillation strategy already used in MEMS. So there are large scope to use this self-excitation technique in a MEMS resonator. Like you can extend this work to a multi degrees of freedom system or a continuous system. You can use different control strategy. Here only stiffness switching control strategy has been used. There may be other control strategy you can develop. Also, you can develop some adaptive control strategy where you do not have to change the system parameter when you are changing the control gain. It automatically changes the control gain value like that. So there are several scopes for that thing. So this is my objective, and I think all of you have understood basics or little bit of that thing. Now this is the end of this discussion or of this talk. Now if you have any question, then you can ask me. If you have any question, you can ask me from that self-excited MEMS resonator.
Yeah, so it is quite exciting presentation, and we learned many things. Actually, so far, all these presentations are complementing each other. So it is quite nice. So we have learned many things, specifically the nonlinear dynamics part and this part. So now the floor is open for taking up any question. Yeah, please. Yeah, I can see many MTech students and those who have studied nonlinear dynamics and will be studying nonlinear dynamics as well. So please ask if you any question. Okay, I think after the lunch they're beat off.
Okay, no problem. That's fine. Okay, and thank you.
No, I'm having few. I'm having few. Actually, you have shown a very interesting topic. Yeah, see those who have studied nonlinear dynamics, I think you have studied Hopf bifurcation and all this. So professor has shown the Hopf bifurcation.
So I have not discussed in details.
Yes. No, it is expected. So he has talked about the Hopf bifurcation. It is quite. I mean, the talk is very interesting. I mean, it is just actually I have enjoyed the talk, complete talk. It's very interesting.
Okay,
very interesting. And the thing is that, sir, we have also, like you are doing for the heaviside function, we have done it for signum function, the excitation.
Okay.
We have given the
Okay.
excitation and the control of
Okay. Okay.
the signum function, and we have achieved the same limit cycle oscillation.
Okay.
It is
Fine.
true. I
Hmm.
mean, people, why they don't use this self-excited or these kind of, actually, you are getting of its own. The nature you are getting, that it is the system developed nature.
Hmm.
And what we in the control strategy we have given is that we have given the actually we are switching.
Switching. That's all. Only we are switching.
Yeah,
On
switching.
off fashion.
So
Hmm.
we also got the same limit cycle oscillation. And the thing is that actually there are few MTech students. The previous batch student, he has published one paper onto this,
Okay. Okay.
just with the switching, only
Okay.
switching. We have
Hmm.
given the switching, and this electroactive. Actually, sir, this session is related to the electroactive things, magnetoactive things, and
Uh,
MEMS
uh,
things, because they
uh,
are all sister and brother.
right. Right.
So, so they have got the idea. They have got the idea, and really, it is quite. I mean, very interesting. Very interesting.
Actually, sir, in MEMS, the application of this self excitation is very less in research.
Yes, yes.
So if we can use this switching technique in a electric circuit with the help of the mechanical component, and that will be very useful. So that thing I have only the stiffness switching I have worked on that thing. So there are several advantages I have said. So we can use or we can extend this work. There are so many scope to use this technique in a MEMS. MEMS. Also, I have said you that to generate chaos. Actually, it is very easy to generate the chaos with self-excitation technique. So,
Absolutely, sir.
uh,
The thing is that if you just change the polarity, we have seen that we have, if we are going to change the polarity, means instead of giving it the positive feedback or negative feedback. So we, in one case, we are getting the limit cycle oscillation. In other case, we are getting the yeah, chaos.
okay.
So for the negative feedback, we are getting limit cycle oscillation. In the positive
Hmm.
feedback, we are getting chaos. I
Chaos.
mean,
Okay.
nonlinear world is so interesting and appealing, such that
Uh,
I mean, it's just appealing. You can't
right.
resist. You can't
And
resist.
it is all times it is not predictable. That means if you say that it will follow the same rule and same way, it is not like that. It may change the rule like that.
Okay. Bah, good. So it was a very nice presentation. Let's thank the speaker. And I think if you have any question, you please feel free to ask. Or otherwise, these recordings will be there. So you can refer to your friend. And if
Also,
you want,
there is my mail ID is in the website. If you have any queries about this thing, about this topic, you can ask me. There will be no issue. Okay.
actually, sir, let me conclude this way, that
Mhm.
this workshop is a scientific social responsibility fund. That means we are supposed to convey our message of this field to the students, the researcher, faculty members, and whoever is interested. So that is why we are recording this, and we are asking the participants to spread those recordings if they need it. And in fact, you just make these with these recordings, whatever the way you want to explore the entire physics that you can do. And let me conclude this session and the entire workshop in such a way that in the first lecture, we have got the mathematical idea. Actually, that speaker was from mathematical background, mathematics. So she gave the nonlinear dynamics. And in the next session, we got Professor. Uh, we got the first speaker was Dr. Kriti Arya, and the second speaker was Dr. Anand Bhushan. So he has gave us the idea about the MEMS thing, and we over there we have seen that the electric action is going to work in a certain way, that the same way as that of the electroactive material is going to work. So we got the idea from Dr. Anand Bhushan, and it was a very nice presentation. Next, we got Professor Prashant Saxena from University of Glasgow. So he gave us the magnetomechanical coupling, and it was a very nice thought opening. He discussed about many stability, and the stability which he introduced with us quite new. That is the necessary and sufficient condition of stability, which is quite unique. And that is what is the major takeaway. And I think, including him, all these experts have given the idea that there are many scopes of work, many scope of work at this emerging field, and that is what he has conveyed to us. Next, we got Professor Deepak Kumar from NIT Bhopal, and he gave us the not this mathematical jugglery, though he did his PhD in mathematics, mathematical world, but he gave us the idea of the experimentation things. Next, we got today Dr. Aman Khurana from IIT Indore, and he gave us the mixed, the mathematics as well as the practice experiment. So it was a very nice, eye-opening presentation. Next, we got Dr. Atul Kumar Sharma, who is from IIT Jodhpur, and he gave us the complete fundamentals. That means from the scratch, how you can build up, which is quite eye-opening. And next, today's session is concluded by Dr. Anindya Malas, and he gave us a very interesting topic in nonlinear dynamics. Actually, all these together are going to create the different flowers, and the main garland is that thread is taken care by the ANRF, Anushandhan and Research Foundation. So the ANRF is the bonding things, and we got various experts. They are established in their own field, and they have given their valuable time with us, spent a valuable time with us, and give us the beautiful lecture. And we thank all the speaker. We thank all the audience for their continuous patience and support. So thank you, and we conclude today. And your participation certificate will be shared in this page, in this team page, and with the WhatsApp group. So thank you all. Thank you, Professor Malas, for your
Okay,
time.
thank you, sir.
And if the participants are having any query, please feel free. And most importantly, the recordings are there. You can refer, you can download, and you can refer. Okay, then. So we can
Okay.
leave now. Thank you. Thank you,
Okay.
Professor.
Okay. Thank you, sir.
Have a good
Thank you.
day.
Thank you, sir. Okay, sir.
Thank you. Thank you all. Have a good day. Thank you. Thank you. We are